All right, welcome to 4.8, L'Hopital's rule for indeterminate limits. All right, so the indeterminate form of some things, you might be familiar with that phrase. That is the idea of things like 0 divided by 0 or infinity divided by infinity. These strange things that happen in math that we're not really sure about what to do. Um, it gets just kind of weird. So, like 0 divided by 0, let's just start with that one. We have a couple different rules that can work out. Like 0 divided by anything, like 0 divided by 5 is 0. That makes sense, right? So is the answer 0? Well, you can't divide by 0. That was a rule, if you remember that. So we can't do 5 divided by 0, so I should be able to do 0 divided by 0. We also have the rule of like 5 divided by 5 is 1. So 0 divided by 0, should it be 1? Well, we don't really know. That's why we call these things indeterminate form. Okay. So when we're doing limits that have this indeterminate form, we wind up getting stuck. Okay. So if you remember, we've done a limit like this before. The limit as x approaches 2, if we try to just direct evaluate, 2 squared is 4, 2 times 5 is 10, 14 minus 14 is 0 over 0. Right? So we had to do something like factor, potentially. 14 is 7 and negative 2. The minus 2's will cancel. So we can now evaluate 2 plus 7, that's 9. All right, so this answer did have a limit value. Great. Okay, but that just took a lot of work. Okay, and if you remember some of the limits that we did way back in chapter 2 with all the square roots and things like that when we were first learning a derivative, those were pretty tough. Okay, and a lot of them were in this indeterminate form. Okay, this 0 divided by 0. But then we just did some limits in 4.6, those asymptotes that were also pretty hard when you had like infinity over infinity, if you remember those ones. So we have this wonderful rule called L'Hopital's rule that can help us do these. Okay, so the general idea is if you ever have two functions that when you evaluate their limits, they both become 0. All right, so the limit as x approaches a of our f function and our g function, if these are both 0, so we get that 0 over 0 idea, if you get that as an answer, 0 over 0, it has to be that, okay, you can do L'Hopital's rule. L'Hopital's rule says the limit is still the same value if you take the derivative of the top and the derivative of the bottom. Okay, so let me explain. So, good example. One we just did. We just got this answer. This answer was 9, right? So L'Hopital's rule says, hey, if you plug in the 2, all right, we do wind up with that 0 over 0 idea, right? 2 squared 4, 5 times 2, 10, 4, 10 is 14, 14 minus 14, 0 over 2 minus 2, 0. All right, hopefully we're good there. So L'Hopital's rule says if you get this, then what you can do is take the derivative of the top, 2x plus 5, the derivative of the bottom. Now try to evaluate, right? Well, now am I allowed to plug in 2? Yeah, 2 times 2 is 4 plus 5, that's 9 over 1. That's just 9. All right, so instead of having to do all of this factoring or what we did in the past of like multiplying by conjugates, we did a whole lot of work with these limits, but we didn't know derivatives then. L'Hopital's rule allows us to just take the derivative of the top, take the derivative of the bottom, and the limit will still be the same value. Okay, and that is it's huge. It's so helpful. All right, but this is also why when we were doing limits, you may have, if you looked up an answer at some point, this limit right here is super easy to do during L'Hopital's rule, but kind of hard to do, like how we originally learned it. We didn't know derivatives, so we couldn't do L'Hopital's rule when we don't know what a derivative is yet. All right. So the idea is now that we know those, we can apply them. All right. So if at some point in time you lost some points on a homework or a test, God, I hope you didn't do that on a test. But if you lost some points on the homework, the review, or you looked up an answer and they just went straight from here to here and said apply L'Hopital's rule. Well, until we know this, until we have a good grasp of derivatives, we can't use that. All right. And so I will admit that's why a lot of times, like using Mathway or Photomath or anything else that we have in today's world, they don't know what you know. Okay, they know so much more and so many more techniques that might make the problem really easy. But if we haven't got there, we can't use it yet. All right, so we've done this limit a couple times. We've done it with a table. All right, and that was the only way we could really do it before. We did a table for this way back when we were first learning limits. If we plug in 0, sine of 0 is 0. And 0 for x, so we get that 0 over 0. Now, you have to show me when you do these things that you do, in fact, get that indeterminate 0 over 0. All right, so we can apply L'Hopital's. Derivative of sine is cosine. Derivative of x is 1. Now, can you plug in 0? Absolutely. Cosine of 0 is 1. So our answer here is 1. L'Hopital's rule makes that very, very quick, easy, pretty painless. You do, again, have to show me this part first, or else you just can't apply L'Hopital's. Okay, only words for that format. All right, limit as x approaches infinity. All right, can still do those. E to the 1 over x. Well, that would be e to the 0. 1 over x at 0. Well, right now I'm not at 0 over 0. But e to the 0, that's 1 minus 1. Okay, now I've got my 0 over 0. All right, so if you get 0 over 0 by trying to evaluate a limit, you can apply L'Hopital's rule. It doesn't matter that this one's the limit as x approaches infinity. It still works. All right, so the derivative of the top. Well, the derivative of e to the 1 over x is e to the 1 over x times, I have to do the derivative of, the chain rule here. All right, so the derivative of 1 over x, that's like x to the negative first power. So that would be what? Negative 1 x to the negative 2. Derivative of the bottom, that's also x to the negative 1. So that's negative 1 x to the negative 2. Well, this is nice. That's going to cancel. All right, so we are just left with the limit as x approaches infinity of e to the 1 over x. That is e to the 0 over 1. Right, as x approaches infinity, this would be 0. All right, 1 over infinity, that's 0. And so e to the 0 is 1. All right, if x is 0 here, sine of 0 is 0 minus 0 over 0. So yeah, we get that 0 over 0. So we apply L'Hopital's rule. We plug in 0. Cosine of 0, that's 1 minus 1 over 0. Oh, Lord, we got it again. Well, the beauty of L'Hopital's rule is that you can apply it again, and it still works. So we try it again. Derivative of cosine is sine. Derivative of 1 is 0. Derivative of 2x is 2. So plugging in 0, we got 0 over 2. All right, so this answer is 0. We got 0 divided by 2, and you can do 0 divided by 2. That is, in fact, just 0. Okay, so L'Hopital's rule, really nice. Now, it does also work in the case of infinity over infinity. Okay, so it doesn't have to be 0 over 0. It can be 0 divided by infinity. So if you try to plug in infinity, it would be what? Infinity over infinity. Yep, I've got it. Okay. What we learned in the past was that we'd have to divide everything by like an x. And that got really messy, if you remember. So we'd have to do like, 3 plus 5 over x, 2 plus 1 over x. Limit as we approach infinity. So it was 3 over 2. Okay, the L'Hopital's rule says, hey, we got infinity over infinity. All right, let's just take the derivative. Derivative of 3x plus 5 is 3. Derivative of 2x plus 1, that's 2. Well, there's no more x values. So I got 3 over 2. Way easier than having to divide everything by that highest power thing. Okay. All right, the next one, if I put infinity squared, that's infinity. E to the infinity, yeah, that's infinity. All right, so we apply L'Hopital's. 2x over e to the x. Plug in infinity, we would still get infinity over infinity. So we try it again. 2 e to the x, plug in infinity. This is really big. 2 over infinity. Well, that is 0. All right, so we can do that. Plug in infinity. Natural log of infinity is infinity over infinity. All right, so we apply L'Hopital's. Derivative of the natural log is 1 over x. Derivative of 5x is 5. Plug in infinity, we got 0 over 5. And we got 0. All right, so it can work. We can do that. Now, again, you can only apply it in those two special cases, only if you have infinity over infinity or 0 over 0. So, for instance, if I try to plug in 3 here, 3 squared, that's 9. 5 times 3, that's 15. 9 and 15, that is what? 24 minus 4, that's 10 over 1, 10. But like, if you're just not paying attention and you don't get that 0 over 0 thing, and you just try to do it, 2x plus 5 over 1. If you plug in 3 now, 6 plus 5, that's 11. Okay. So if it doesn't give you 0 over 0 or infinity over infinity, you can't do the derivative of the top and the bottom. Okay. It only works for those special cases. Okay, so don't do it if you don't get infinity over infinity or 0 over 0. All right, so again, you have to get 0 over 0 or infinity over infinity. So what happens if you don't have that, but you get one of these other weird things? Okay. Well, if you get one of these weird things, your goal generally needs to be to play with it a little bit. All right. Some clever manipulations I have written here. Okay. For instance, if we try to plug in 0, but only from the right, I hope you know you can't do the natural log of negative numbers. You can't do the natural log of 0 even. But if you try to do that, so if we plug in a number very, very close to 0, okay, very, very close to 0, but positive, we'd wind up with 0 times the natural log function. If you graph it, it kind of does one of these things. There's a vertical asymptote at 0. So this becomes 0 times negative infinity. Okay. So the general idea when you have something very close to 0 times something really, really big, well, a couple different things could happen. All right. Take a really, really big number times a really, really small number. Well, I don't know what's going to happen. It might still be really, really big. It might turn into 0. They might kind of cancel each other out in some form or another. Okay. A really, really big number like 5 million times a really, really small number like 1 over 5 million cancels out to just 1. Okay. So depending on how these two things relate to each other, they might produce a couple different answers. Now, this doesn't say 0 over 0 or infinity over infinity, so I cannot apply L'Hopital's rule right away. But what we can do is, as I said, some clever manipulations. All right, leave the natural log. But this thing, I can move it to the bottom of a fraction. All right, to move it to the bottom of a fraction, I just have to make its exponent a negative. Okay. Now, if I plug in, or I guess if I look at this thing, I have, if I put in 0, okay, well, I guess what is x to the negative first? that's like 1 over x. So now if I put in 0 here, 1 divided by something really close to 0, well, 1 over something really close to 0, that's going to make a really big answer. Now I have 1 over infinity. All right, so now I can apply L'Hopital's rule. I've got an infinity over infinity. So by moving this to the bottom of a fraction, making its exponent negative, I've created an infinity over infinity situation. So I can apply L'Hopital's. The derivative of the top, the derivative of the bottom. Now I can move this back up to the top. The x's can cancel. So this is just the limit as x approaches 0 from the right of negative x, and no more fraction, right? The -1 and the 1 just made a negative. All right, and so this answer is in fact 0. All right, limit as x approaches 0 of 0 or x times cotangent. All right, cotangent of 0, I don't know if you know that. I don't know if I remember what cotangent even is. Cotangent is 1 over tangent of 0. Okay, so that gives me an error. I can't do that. Okay, so it's either a 0 or it's infinity, one of the two. Okay, so I can't do that. But it's not 0 over 0 or infinity times or over infinity. Do you remember what cotangent means besides 1 over tangent? Well, cotangent is cosine over sine. Now if you plug in 0, 0 times cosine of 0, 0 times 1 over 0. Well, now I have 0 over 0. So by calling cotangent what it is, I've manipulated it to produce a 0 over 0. Now I can apply L'Hopital's rule. Derivative of sine is cosine. This thing, I've got to actually do a chain rule. All right, so it would be cosine of x. Derivative of the first is 1 times the second, plus x times negative cosine. Derivative of cosine is negative sine. So now when I plug in 0, all right, cosine of 0 is 1. 0 times 0 over 1. So we wind up with 1 from this thing. All right, next step. If I try to plug in 0, I get 1 over 0. Can't do that. And 1 over 0. Can't do that. All right. Now, that's not 0 over 0. So I can't apply L'Hopital's rule to these. Okay. But what we can do in a situation like this, in fact, it'd be more like infinity minus infinity. Okay. 1 over 0 is really big. Okay. 1 divided by something really small produces something really big. So I kind of have an infinity minus infinity. Okay, so what we can do is try to just combine these. Do you remember making like terms, common denominators? All right. So now if we plug in 0, so we have sine of x minus x over sine of x times x by getting a common denominator, combining the two numerators, leaving the denominator the same. Now if we plug in 0, it would be 0 minus 0 over 0 times 0. Now I've got 0 over 0. Now we can apply L'Hopital's. So it would be cosine x minus 1 over, I have to do a product rule, cosine x times x plus sine of x times 1. We put in 0. That would be 1 minus 1 over 1 times 0, 0 plus 0 All right, and so we are still stuck with a 0 over 0. So we apply L'Hopital's again. Derivative of cosine is sine, and derivative of 1 goes away. Derivative of cosine is sine times x plus cosine times 1 plus cosine. All right, we try putting in 0 again. I got 0 on the top. 0 times 0 plus cosine of 0 is 1 plus cosine of 0, that's 1. So we wind up with 0 over 2, all of that to say a good old-fashioned 0. All right, so this one might have been a situation where just doing a table might have been the easier method here than doing all of that L'Hopital's rule. All right, next up, last but not least, when you wind up with one of these other weird things, 0 to the power of 0, all right, 1 to the power of infinity, or infinity to the power of 0, okay, we have some different methods. Okay, these are also called indeterminate forms, but they're just a little bit harder to figure out. Okay, so like if you plug in infinity here, you'd wind up with infinity to the 0 power. Okay, so like what is that? Do a really, really big number, but raise it to the power of 0. What we kind of learned was that anything to the power of 0 is 1, right? But infinity to any power should be really big. Okay, remember these are limits, so like it's not actually 0 and it's not actually infinity. So like the bottom number's getting really big, but the top number's getting really close to like 0. I don't know, it's weird. Okay, so the method that we employ here are logarithms. Okay, so if we say that this is equal to some limit L, let's put that over here. Then what we can do is apply a log, preferably like a natural log. And we can kind of sort of do the natural log of both sides. Okay. Well, if you remember natural logs, numbers inside can move to the front. All right. And that limit now, when we do this limit, it would be 1 times the natural log of x, and x is going to infinity. The natural log of infinity is infinity over infinity. So now we've created an infinity over infinity situation. So we can apply L'Hopital's. So L'Hopital's rule says take the derivative of the top, divide by the derivative of the bottom. All right, put in infinity, and we wind up with 0. Okay, 1 over infinity, that's 0. 0 divided by 1, that's still 0. So we're saying that the answer to this is 0. Remember, we took the natural log of our limit. So the natural log of the limit is 0. Well, I don't want the natural log of my limit. I want my limit. Natural log is log base e. So the limit would be e to the power of 0. Remember, base, answer, exponent, maybe. And e to the 0 is 1. All right, a graph might be a good idea to take a look at for this thing. Okay. Our function was x to the power of 1 over x. Weird. And a graph makes this actually just look so incredibly easy. We're doing the limit as x approaches 0. And look at what happens as we get closer and closer to 0. For an x value, the y value is right there at 0. Okay? And so that's where this is coming from. Oh, no, gosh, I said the answer was 1. Because we're doing to the infinity. Duh. Wrong direction. Go this way. All right. As you get closer and closer and closer to infinity, Look at the y values now. We're getting closer and closer and closer to 1. We weren't doing the limit at 0. All right. We could have. All right. If we did this as, hey, look at that, as we go to 0, there it is, something really similar. As we do this one to 0, we can't do 0 to the 0. That's an indeterminate form. So we can take the natural out of both sides. Sorry, we call this the limit L. We take the natural out of both sides. This can move to the front. All right. 0 times 0, actually this should be 0 times negative infinity. So we can't do L'Hopital's yet. We have to, again, do that little adjustment. Move that x to the bottom of the fraction. Now if you plug in 0, remember this would be one over it's on the bottom. Okay. Now if you put in 0, we would wind up with negative infinity over negative infinity. Actually, that's probably infinity. So now we have that indeterminate. Now we can do L'Hopital's. So we'd wind up with 1 over x over negative 1x squared to negative 2. So 1 over x times, so this is negative 1 over x squared. So times x squared over negative 1. Okay. Same change flip. So our x and our x squared. And so we wind up with 0. Okay. Again, the natural log of our limit is 0. So our answer is e to the 0 equals L. So L is 1. All right, and our Desmos graph should agree with that. Equation this time was a little different. All right, so notice this graph as x approaches 0 is right there at 1. Okay. All right, so that's the general idea with limits. L'Hopital's rule, but you have to have those indeterminate forms in order to apply it. And when I say you have to have it, I mean when you do your homework and things like that, you have to show me that you did in fact get that 0 over 0 before you apply it. All right, you can't just straight apply L'Hopital's rule right away. All right, like right here, we can't just apply L'Hopital's rule because we don't know what we're doing. You have to get it into the right format first. Okay. Show me that you got 0 over 0. Show me you got infinity over infinity before you can apply it.